Hello everyone. Next, let's go through the major components inside of the operating system: the process, the main memory, the storage, the I/O, privacy and security, etc. Okay, let's first look at the process. So basically, the process is defined as a program in execution inside of the computer system. So if you may wonder, okay, Dr. Wang, what is the difference between a process and a program? So basically, program is the binary stored inside of the hard disk. So it is a passive one. And also, on the other hand, a process is the program which is loaded inside the main memory and executed on the CPU. So it is an active one. So basically, the major difference between process and program is passively stored in the storage, and the process is actively executed inside the computer system. And also from here, you can tell sometime it may happen, although we only have one copy of the program stored in the hard disk, we may have multiple copies of processes executed inside the computer system. For example, if you are doing word processing, you may open multiple Word files at the same time, right? So each of them is a process of the Word program. Then you can see we only have one copy of a Word program stored on the hard disk. However, we have multiple word processes that are running inside the computer system. And another thing is that process is often the smallest unit inside the computer about the programs running inside the computer. And later you will see some program may even have multiple processes there. However, basically that is one complete copy, one complete unit inside the computer. So it cannot be further divided. If you further divide it, it is not one complete program there. Okay, and also for the process to run inside the computer, it actually needs different kind of resources so that it can be eventually executed and accomplish its task. So examples of the resources it needed include the CPU. Surely it must be run on the CPU to making progress. It also needs the main memory to temporarily store the data and also the code, the binary code for the process itself. And of course, it may need to do some I/O, so may need to access the I/O, and sometimes, and also it may need to read the data from the file and also write the result back to the files. So that are the typical resources may be required by a process. And of course, the process also needs some initialized data to start its execution. For example, it needs to initialize all the array defined in the program and also put some initial value for certain variables so that the process can start execute properly. And also, since while its execution, it needs to occupy some resources, and of course, when the process is terminated, either it finish its running or it get into some error, the operating system decided to kill it. In either way, at the termination, we need to take those resources back. We need to get back the CPU, the assigned memory, also the I/O and the files, so that those resources can be used by other processes later. And also remember, like I mentioned previously, inside the nowadays computer system, we have many processes inside the computer system nowadays, so that they run in concurrently inside the computer system. For example, inside your computer, you may open the web browser process so that you can watch this video online, and also you may open a word processing software to taking notes, And also, you may also open an email processing process to help you to receive email from the background, right? So typically nowadays, all the system has many processes running inside concurrently. So remember, that is what happened for nowadays process in the operating system. Since we have multiple processes running inside the computer system, so one major task the operating system needed to do is to do the process management so that all the processes can be managed properly and they run in a good condition, making good progress, and eventually finish their tasks there. Okay, so here in this slide, list some major management an operating system needed to do. For example, to carefully schedule different processes on the CPU. Remember, CPU is always the most scarce resources. Even with multiprocessor architecture, we may still only have a very limited number of CPUs, where most time the number of processes is much larger than the number of CPUs. Then we need to schedule those processes on the CPUs carefully so that all the programs are still responsive and also they can still finish running quickly and efficiently. And also, when the user newly click a program on the screen, the program needed to become active and start to run on the computer system. That corresponding to the operating system's job to create a process corresponding to the program, and later, when the process finished running, the operating system also needed to delete the process and reclaim all the resources previously assigned to this process. And also sometimes the process may need to do some I/O, or for some reason it cannot get onto the CPU, so then the operating system also needed to be able to temporarily suspend those process and then later let the process to be resumed to keep running on the CPU. And also, sometimes different processes may need to communicate with each other. And then we need to better synchronize those processes to make them work properly. For example, while you are doing the word processing, there will be a front-end process response to your typing and show the result on the screen. There is another process on the background may periodically keep saving the data you just type in into the hard disk to make a backup in case something wrong happens inside the computer system. And then these two processes, they need to work in a collaborative way and they need to be better synchronized so that they won't mess up with each other. And most time, those synchronization is done by process communication. So again, that's part of the job the operating system needs to help them to do. Especially, not only the processes within the same computer, they need to communicate with each other. Sometimes the processes on different computers, they also need to communicate with each other. One good example is while you do the web browsing. You have a web browser process running on your own computer and also have a web server process running on the server so that the two processes can communicate with each other. The client process sends a request to the server process, then the server process access the data on the server and then send the response back to the client process, and then the client process can show those data on the screen. You can see in this example, actually the two processes are on different computer, and then they still need to communicate with each other, and that is also part of the job the operating system needs to help with for the process management. Okay, we have talked too much about that in this slide, and don't worry, later we will have one chapter dedicated to introduce all those things in more details. Besides the process, another major component inside the operating system is the main memory. Basically, to execute a program to make it running on the CPU as a process, we must have its instructions available in the main memory, and also we must have the corresponding data also be available on the main memory. So basically, how we need to do is we need to manage the memory so that we can determine what should be in the main memory and at what time point, so that we can better optimize the CPU utilization and also make the computer have better response to users. One good example is you can imagine while this program is on the CPU, it wants to execute the next instruction. However, if this instruction is still stored on the hard disk, definitely we need to wait for a long period of time to wait the instruction being loaded into the main memory and then loaded to the CPU, then to be executed, right? So if we do the memory management well, then those instructions should already be available inside the main memory. That definitely can increase the speed for the program to be running on the CPU. So that's why memory management is very important. And another thing I'd like to mention is for nowadays, I'm not sure whether you know how large is the Windows operating system, or if later maybe some of you play a PC game, I'm not sure how much whether you know how large a typical PC game can be. Most time they can be pretty large and much larger than the full size of the main memory, which is sometimes 4 gigabytes, 8 gigabytes, or 16 gigabytes, right? So another thing is, then you can see most of the time nowadays large program, they cannot be put in as a whole inside the main memory. So another duty or another job the main memory management need to do is, okay, in this case, we need to determine which part of the program currently should be put into the main memory. And also later, we should switch which part out, then take some new part of the program into the main memory so that we can do it in the way it can facilitate the program being run on the CPU to maximize the efficiency and the CPU utilization there, and also provide the user the best responsiveness. Okay. In particular, memory management needs to do the following jobs. First, it needs to keep track of which part of the memory are currently being used and by who, so that if your data is put in the main memory, it won't be overwritten by other process, right? So it won't be kicked off by accident. As long as you need those data, then it will be put into the main memory. And only your program, your process can access those data, not someone else's process. And also, it needs to decide which processes or which part and also which part of the data need to be moved in and out of the main memory. Again, if you still remember my example from the last slide, because currently program is too large than the memory size, then surely the operating system need to decide at which time point we should put which part of the program into the main memory and move which part of the program out of the main memory. And also because we have many processes inside the computer system, running inside the computer system, sometimes the aggregate size can be even larger than the main memory size. In that situation, we sometimes also need to move some process out of the main memory temporarily to let the main memory is enough for the remainder process to run, and later then we move those process back on the main memory so that they can be further executed on the CPU. Okay, so this is the second task. And also, while a process is running, it may dynamically need more memory space. maybe at the beginning it only needs a small size, but later it needs more larger size to be executed running on the CPU. Then in this situation, the operating system needed to be able to dynamically allocate some additional memory space to the process, and also later when the process don't need those memory space, you may want to dynamically deallocate those memory space so that those space can be claimed and reused by other processes even before this process finish its running. And since you are in this course, you will do C programming, and actually later you will have a chance to use C programming to do those operations, to dynamically allocate some memory space and also free those memory space later when you don't need them anymore. Okay, again, here is just a quick summary, and later we will have chapters to dedicated explain all those memory management operations in detail. The next major component is the storage. Basically, the operating system needs to provide the user the uniform and the logical view of information storage. So you already know this. What is this uniform logical view? Basically, it will abstract the physical property of those data inside the storage to a logical storage unit, a file. So basically, no matter where you store those data, maybe on a solid state disk, on a hard disk, maybe on a tape, or on a CD or on DVD, no matter what physical medium you are using, what you see from the operating system about those data, they are the same. They are just one file, right? How can this happen? Because operating system help you to do so to hide a lot of details there. Because each medium is controlled by different device controller, and there are a lot of details there. For example, for the hard disk, I'm not sure you know, we need to know the rotate speed, and we to know where the data is inside of the disk sector, so that and on which track, so that we can find and locate the exactly location of the data on the hard disk, so that we can get the data out or write new data in. But you don't need to worry about that. As long as you tell the operating system, I want to read the data from this file or put the data into this file, then operating system will help you to do all the detailed, dirty work there. Okay, so that's one thing about the job for the storage management in the operating system. And also, above the file level, the operating system also needs to further manage those things at the logical view, not only inside the physical level, the physical view. So at the logical view, the operating system further needs to do the file system management. For example, the files often need to be grouped into directories, right? Especially nowadays, if you only have one or two files, three files, that's fine, you just put them under one directory. But what if you have 1,000 files? And those files are for different purposes. Some may be your personal data, your personal diary, some may be for the course 423, some may be for other courses. Definitely, you want them to be better organized, right? So that's where you need to use the directories. And again, who help you to maintain those information? The operating system does. And of course, sometimes there may be multiple people use the computer system, and surely you don't want others to access your own file, right? Even it's not your personal private information, maybe you just put your writing assignment of this course in this folder, still you don't want anyone to just copy paste it, or maybe even someone just delete your assignment, later you cannot submit it on time, right? So that's another thing the operating system needed to do so for the file system management is to have the access control, so that to make sure only the right user can access the right file at the right time, and avoid any other mistakes happening. This slide lists a number of operations the storage management needed to do. Again, for example, the operating system need to help us to create, delete files, and also directories, and also need to provide the primitives to help to manipulate the files and directories. For example, to set the files to read only, and maybe later to make it back. And for some system files, we need to be able to hide those files from normal users so that users won't mistakenly delete or change those files, right? And also, operating system need to help us to map the logical view, the file, onto the secondary storage on those physical hard disk, so that we don't need to care about those details when we write the program and access the data from those storage. And also, sometimes in the server, we not only need to store those data on the hard disk on the server, we also need the operating system help us to periodically back up those files on the stable storage media, for example, on the tapes or on other remote network hard disk, so that even later the server fails or the hard disk on the server is down, we can still recover the data from the remote safe backup storage, and then everything will go back to normal. So all those things need to be done and handled inside the operating system. And again, here is just a brief summary. We will revisit those things later in later chapters. Another important management related to the main memory and storage is the caching management. If you still remember when we talk about the storage hierarchy, so basically that allow us to apply the caching mechanism there. And however, who should manage those caching mechanism? Operating system should. So basically, in the caching management, we need to consider two design issues. First is the cache size, and the second is the replacement policy. We all know the cache is faster than the original storage. However, it is more expensive, so it is often smaller in size. Then, how much size do we need? If we want the cache size is equal to the original storage size, that's too expensive, and surely we don't want that. But if the size is too small, then each time when we need to access some data, we find we don't have enough size in the cache to hold this data. We have to kick some old thing out to load this in. However, when we need to access something else, then this one have to be moved out. Then later, when we need to access this one again, we find it is not in the cache anymore, then we have to reload that from the original storage, right? So that's not something we want, which means if the cache size is too small, it will still not work well, right? So that's why we need to consider the cache size as a design issue. Another issue is the replacement policy. No matter how you choose the size of the cache, unless it is equal to the size of the original storage, otherwise, eventually the cache will be filled up. Then, when you get some new data in, you have to choose which one should be take out. Then you need to make the decision carefully. You can imagine, if you choose to take this old one out, however, it may happen right in the next period, the process needs to access the one you just take out. Then you have to take it back. Of course, there will introduce additional overhead. On the other hand, if you choose carefully, you can choose to take out the data that won't be used for a pretty long time in the future. Then you can see the whole thing would still work correctly without any problem, and the program won't bother to need to take the data back for a long time. Then again, you improve the efficiency, and so that's why the return policy is also some design issue you need to carefully consider when you do the caching management. And also, like I mentioned, caching mechanism can be generalized to a lot of places. So to the main memory, the register can be considered as a cache. And also to the hard disk, the main memory can be considered as a cache. So this can be generalized to a lot of places. But no matter how this is generalized, there are one important thing you need to be careful. This is a cache coherency. Basically, it's because if there are multiple processes, they try to access the same data in the original storage. Since now this data is cached in the cache, where each process may have its own cache. For example, the data in this slide, the data A is stored in the hard disk. However, it will be loaded into the main memory to be accessed by process S. And there may be another process T, who also need to access data A. So another copy of data A will be loaded into the main memory space assigned to the process T. Maybe I just draw a picture. So this is original A in the hard disk. And then we have the process S and the process T. And this is S main memory, this is T's main memory. So a copy of A will go there and a copy of A will go there. However, now what happens is S actually update the A in the main memory and make it become A prime. However, now A prime is only stored in the main memory and is not updated in the hard disk. Now you can imagine, if the process T want to work on the A maybe change it to another value, to A equals to A plus 1. And then again, the result will be put into the main memory of the process T, and then if this is later write back to the hard disk, then you can see this update will get lost. So basically, we need to be careful about this issue when we do the caching management, and this is called the cache coherency. Basically, multiple processes try to access the same data in the original storage, and however, when they access their local cache, then if any process changes those data, then you need to be careful. You need to make sure all the remaining processes be aware about that. Otherwise, we will have the cache coherency problem. Another major component inside the operating system is the I/O subsystem, and the operating system needs to do the management there too. Basically, the operating system needs to hide peculiarities of hardware devices from the user, so that it would be easy and convenient for the user to use them through the operating system. For example, we have different I/Os. You can imagine the keyboard, the mouse, and also, for example, the network card. And the different I/Os, they have totally different features. The keyboard can be pretty slow. You can see no matter how fast you type, maybe in 1 minute, you can just type maybe 1,000 letters, or maybe perhaps more than that. However, the network card, it can be very, very fast. And maybe in 1 second, it can deliver to your computer maybe 10 megabytes of data or even 10 gigabytes of data, right? And then the operating system will need to hide all those different features to make them easy to be used by the user. For example, The I/O subsystem management needed to be responsible for the memory management of the I/O, including buffering, caching, and spooling. For example, if there are 10 gigabytes of data come from the network and into your computer may not have enough time to deal with them immediately. Then those data need to be temporarily buffered in the main memory or in the network card until the CPU become available to process those data, right? And for the caching, again, since the speed of the hard disk or the keyboard is slower than the main memory, than the CPU, if you keep reading or writing data out, we may need to cache them temporarily so that later when you need to revisit those data, you don't need to go back to the hard disk. So this is a caching. And for the spooling, a good example is if there are multiple processes, they want to print something on the printer at the same time. Then surely you don't want the data from two processes to be printed on the paper interleaving. That basically will mess up what's being printed out. Surely you want one thing being printed completely, then the second thing being printed. So that is called spooling, so that it can help you to achieve this, and this is done by the operating system. And another thing is when the user want to directly access those I/O, operating system need to provide a general device driver interface so that the user can access those I/O through this general interface conveniently, don't need to care about too much details inside the hardware. And then who handles those detailed hardware? Surely the operating system. And don't worry, the drivers will help the operating system to do those things. And the operating system can further give the task to the driver, which will control the device controller and help the operating system to do the real job there. Besides those major components inside the operating system, another two important issues in the operating system is the protection and security. Basically, for the protection, it means we need to have control access of processes and users to resources defined by the operating systems, so that we can make sure, okay, when some process want to access some data or to access the main memory or access certain part of the hard disk, whether the process has the right to do so or not. Or when a user want to delete some file, does the user have the right to do so or not? And the other issue is the security. Basically, it means we need to have the defense of the system against internal and external attacks. And you all know nowadays we have a lot of attacks. They try to crash down, try to hack our system. Not to say, for example, the virus, they may they may sneak into our computer, and then later they just suddenly burst out, try to delete our files, crash our system, and make the computer not available to use. And also there may be Trojan horse, other worms from the internet. They come to our computer and try to steal the information from our computer. For example, your bank account and password, and so that the hacker later can log into your online bank and steal money from there, right? So for the operating system, one task is to provide those protection and security features. And to do so, that the first, it requires the system to be able to distinguish among users and to determine who can do what. So for that, operating system need to maintain a lot of information, provide, for example, user identities by the user IDs so that those ID will be protected by password and also associated with those IDs to all the files and processes, so that operating system can tell this file belong to you and this file, the other file belong to someone else. And also, the operating system would define group identifiers to further divide the different rights among different type of users. If you are a normal user, you can only be allowed to do those standard operations. However, if you are a system administrator user, you are in the system administrator group, then you can do more powerful things like install software, delete someone else's file, or uninstall a software, or upgrade the operating system, right? And sometimes, although most time you want to behave like a normal user, but in certain situation, you want to temporarily to do some additional operation there. For example, normally you just want to do writing assignment on this computer, but later you want to temporarily upgrade the word processing software, install a new version there, then you want to temporarily be able to have the right to install new software on this operating system. Then what you need to do is to do the privilege escalation so that you can temporarily grab the right of a system administrator to install the new software, and after that you will give up this right, then still use the system as a normal user. So remember, this behavior is called privilege escalation, allow you to temporarily get more right to have the access to the computer. Inside the operating system, especially the kernel of the operating system, we also need a lot of data structures. The only difference is here the data structure must be carefully implemented to ensure it has the maximized efficiency and also to minimize any possible mistakes or bugs there, because you can imagine if there is the bug inside the data structure in the kernel, and then if the bug happens, then basically the operating system will crash down. It's like, for example, if any of you have used Windows before, especially during the early days, you may already heard about the term the blue screen, right? So it means the Windows crashed and you must restart your computer. So here, similar idea. So you must be careful when you implement those data structure to make sure they are efficiently implemented and bug-free. So here list a number of examples of the quite widely used kernel data structure. You can see most of them are quite similar to the data structure defined in the standard data structure used normally. Again, the major difference is they must be implemented very efficiently. For example, here list some linked list, stack. So remember, linked list basically is implemented by pointers. Later, when we go through the C programming, you will see how we can use pointers to implement the linked list. So basically, each element has at least two things there. So one is the data, the other is a pointer, and the pointer actually points to the next element in the linked list. Okay, so this is a singly linked list, and if you put the last one pointed to the first one, this becomes a circular list. And a double list just have another field to point backward, like this. Okay, and for stack, most of you should know that. So basically, it's last in, first out. So we just push the data into the stack and pop it out from the top. And for queue, it's just the first in, first out. So in queue means we put the data element into the end of the queue, and the dequeue means we get the data out from the head of the queue. And for tree, so again, a very widely used structure. and also the hash function and the bitmap. So if you are not familiar with any of them, you may want to review your course material in the data structure course or search on web. If you still have a question, feel free to ask me. Okay, again, like I mentioned, those data structure, although logically they are pretty similar to the standard data structures, but the major difference is they must be implemented very carefully and efficiently. So for example, in Linux, so most of the kernel data structure, they are implemented in the Linux kernel, and later when you download the virtual machine I provided to you, and you can actually find how they are implemented and defined in the include file, directories, and there actually can find those kernel data structure. For example, this header file is for the linked list. This header file is for the first in, first out queue. And this header file is for a special implementation of the binary tree. With the development of computer system, the computing environment also involved. At the very beginning, traditionally, we normally only have one pretty standalone general-purpose machines. So there, the computing environment is quite simple. You just input data and input code, then it just run, and then it finish running, finish the computation. The output will be right back through the I/O, maybe into the hard disk, or showing on the screen, right? However, now the computing environment become more and more blurred because now most computers interconnect with each other, and also we have some new emerged computing environment. For example, the mobile computing. So if you look at your cell phone, your smartphone, and the tablet, then definitely you can tell there the computing environment is quite different from your desktop computer, right? For example, on your cell phone, it now has much more new sensors. It most time integrated with video cameras, microphones, and even GPS and gyroscope sensor, accelerometer sensor, right? So for example, when you want to use the cell phone to tell you how to get here from the Memphis, then surely it needs the GPS sensor and also needs the accelerometer sensor to locate where you are now and then tell you where to go, right? It even can sense your direction. Now you are facing north, you are facing south, or east west, right? So basically, that's one new emerging things in the new computing environment. And also, now for the mobile phones, you may use Wi-Fi, you may use 3G, 4G LTE, even in the future use 5G for the communication. Again, that is quite different from traditional standard alone general purpose desktop, right? And another thing pretty specific in the mobile computing environment is because in the mobile phone, you may move from here to there, move anywhere you want to go, right? Which means you cannot keep your phone being charged all the time. So again, like I mentioned there, in that environment, you need to handle the battery. You cannot let the battery drain off too quickly. And perhaps most of the people at least expect the battery can support the device for maybe 9 hours and perhaps 24 hours, even several days, right? So you can see in that environment, we have pretty specific communication, wireless communication environment, and also we have more sensors, and which means there the operating system also needed to deal with more IOs, not just the data. You see also the incoming call, the outgoing call, right? And also need to care about the energy efficiency on the battery. And also nowadays, there is another emerging computing environment is the real-time embedded systems. And actually, especially nowadays, if you still remember, I mentioned one of my research interests is the Internet of Things, right? And also the cyber-physical systems. Both of these two things, they are quite closely related to the real-time embedded system. Those systems, they are not run very complicated desktop computer, powerful servers there. They are rather run very, very simple small devices. Even nowadays, a device as simple as an outlet, maybe as a light, there we can have small chip on it, and we can make it intelligent and make real-time embedded system running inside. So there, the design objective may be quite different from the design objective for the general purpose operating system. First, you can imagine, on those small chips, the CPU's computation power is pretty low. Maybe normally, on a normal CPU, it can computation data as large as 64-bit. However, on that simple small CPU on the chip, it may only be able to compute 8-bit integer, add, or subtract, or even may or may not be able to compute multiplication, divisions. Not to say maybe it may not be able to do the floating point computation, right? And another very, very important feature for real-time embedded system is the real time, which means we have strict time constraints which must be met for correct operation. You may wonder, okay, Dr. Wang, why we must follow this? Why we must have strict time constraint? If we only have a small chip on the light, why tell the light to turn on, it turn on. Why tell it to turn off, it turn off. I actually don't care if it takes 1 second, 100 milliseconds, as long as it is not too far along, like 1 day, 1 hour to turn on, that is fine for me. Why you said it is we have the strict time constraint? Yes, for a light turn on, turn off, you may not need such strict constraint, but you can imagine we also have other real-time embedded system. For example, the car. You know that another very hot research topic in the research field is the auto-driving car, right? Maybe in 5 years later, it's not ourselves driving the car, it's just the computer drive the car on the road. Then you can imagine, on the computer system, on the operating system running on those cars, there you need to be very, very careful. Because if the car is driving on the highway, then if some event happens, it must make the decision in a very, very short period of time, and this time must have very strict constraint. And even the computer just be slower than maybe just 5 milliseconds, 500 milliseconds than expectation, the car accident may already happen there, right? So that's another very important feature on the real-time embedded system. It must make the decision in real time, respond to the different events in real time, and must fulfill the strict time constraints most of the time. So that is another computing environment emerging recently. Another emerging computing environment is virtualization. Basically, it allows operating systems, where we often call it guest operating system, to run as applications within other operating systems, where we call the latter operating system the host operating systems. And to do this, we need VMM, shortened for Virtual Machine Manager, running in the host operating system to provide such virtualization services to the guest operating systems. So you may still remember that actually in our class, I provided the Linux C programming environment through the virtual machine, and actually that belongs to this virtualization computing environment, so that we can run one operating system, Linux, on another operating system. So the one inside the virtual machine is a guest, and the operating system who running the virtual machine is a host operating system. Okay, and another computing environment is the distributed system. We already briefly covered that previously when we compared the distributed system with the multiprocessor system. So basically, inside the distributed system, it provides a collection of separate, possibly heterogeneous systems networked together. And so you can see, if you still remember why I talk about that, inside those systems, we have multiple computer systems, and each one runs separately, and their configuration may be consistent, may be same to each other, or may be heterogeneous. And then how they work together, they are networked, so that we use the network as the communication path, and there, most time, we use the TCP/IP protocol. So some of them may already heard those protocol stack, and that is actually also the stack we used in internet nowadays. And also in those distributed systems, actually sometimes we may want to use a very special operating system called the network operating system, which provide features between systems across network. For example, remember when we talked about the operating system previously, we may need to do different management, right? Process management, main memory management, storage management. However, there the management is only confined within one computer. However, in network operating system, all those management must be done among all the systems across the network. So you can imagine how complicated the system can be. And also, how this management can be done, basically through the communication schemes, so that allow different computer systems to talk to each other, so that we can do the management as a big whole thing across the distributed system, so that it can also provide an illusion to the user, or maybe a program running on the distributed system. It feels like itself actually is run in a single computer. So basically, it is not aware actually the network operating system already hide much more complicated things inside it. So it never know, okay, this is actually a distributed system, or I have different computer system running and connected by the network. For a user or a user program there, they may still feel, okay, this is actually one single computer. So this, again, remember this is done by the network operating system. Besides the distributed system, we also have other types of computer network systems. And one good example is the client-server computing environment. There, basically, we have powerful systems such as smart PCs. They run as servers and respond to the request from clients, where the clients often are less powerful devices such as smartphones, tablets, laptop, or even some dumb terminal there. So we have a number of examples here. So if you remember, actually the web service is working in this computing environment, where we have web server provide you different web pages, and there you use the web browser as a client, send a request to the web server, and download a different web page and show them on the screen. And you can see web browser can be run on very simple and less powerful device, even as a very simple cell phone there, right? And also there are other type of client-server computing environment like compute server system. There, basically the server mainly provides the services for computation. For example, if you need to run something, this is especially the case in scientific computing. You submit the job to the server. There, the server do the computation, and then it will return the result to you to the client side. And also we may have the file server system, and there you may talk to the server, send a request, ask the server to help to store some file, and also later may tell the server to help to retrieve some file. Again, those files then will be downloaded to the client, and then you can work on the file at the client. Later, when you are done, you can upload the new version to the server again. So that's another example of the client-server computing environment. In general, client-server architecture or client-server computing environment is very easy to understand because different computers have different roles. As shown in this figure, we have a computer serve as the server, and also we may have multiple computers serve as different clients. This also makes it very easy to maintain. So usually the client software is relatively simple and easy to program and easy to maintain, and most efforts only need to be put on the centralized server, so that we can also better make the server running very efficiently. And also you can see in the client-server computing environment, all the multiple clients can communicate with one single server at the same time. However, be careful, those clients, they never communicate with each other. So that's a very unique feature for the client-server computing environment. And we also have a counterpart for that, which is called the peer-to-peer computing environment. There, strictly saying that we have no term of client and server. We only have peer in that environment. But actually, what a peer does is a peer can act both as a client and as a server, which means a peer can request service from other peer. In this case, the formal peer I mentioned act as a client. And also, a peer can provide service to other peer. And in this case, the formal peer I mentioned worked as a server. So in peer-to-peer computing environment, because each server can also provide service to other peer, then you can imagine if we have more and more peers get into the computing environment, then the whole environment ideally can still serve any peer who needs the service, no matter how many peers get into the system. However, if you imagine the client-server computing environment, where we only have one centralized server, if we keep have too many clients come to request the service from the server may be overloaded. Now you can see, compare these two situations, and you may already see one advantage of peer-to-peer computing environment is it has much better scalability. In ideal case, it can support infinity number of users, because when a new user request some service, it may also provide some service to other peers. So basically, it will have infinity amount of capacity to provide the service. And another unique feature compare the peer-to-peer to the client server is, since there we don't have strictly concept on client and server, actually the user, they can communicate directly, connect and communicate with each other. So there is no many-to-one structure pattern like we see in the client-server computing environment. So that's also why it is called peer-to-peer, means anyone can connect to anyone else. And then you may wonder, okay, Dr. Wang, then why nowadays most of the popular software are still based on client-server, not peer-to-peer? Because you can see, because there the connection is quite complicated. We may have much more connections compared to the client-server computing environment, which means it is actually very, very complicated to handle, to manage. So that is a downside, one downside for the peer-to-peer computing. So unless very necessary, most of the time, people still want to start with a client-server computing environment, unless later scalability becomes the most critical issue, and then people start to think about maybe we may want to switch the environment to the peer-to-peer computing environment. And I can give you two examples. And one example is a BitTorrent. I'm not sure whether you heard that or not. That is the typical peer-to-peer file sharing network software. And the other one is Skype. Maybe you used that for long distance telephone. That also is based on peer-to-peer computing environment. And also nowadays, even for Microsoft Windows and Mac OS, when they do the system patch, when you download the update from Microsoft or from Apple, originally those update downloading are based on the client-server computing. However, nowadays, since we have too many users, and also when a very important security update is available, all users want to downloading them. So actually, now the design is gradually shifted to the peer-to-peer computing, where we still have the centralized server in case any computer cannot find any peers currently can provide the new update. It can still download from the centralized server. But when there are too many users want to download the new update, actually, now we change the design there so that a user can turn to another user who already downloaded the update and download part of the update from that user so that to speed the system downloading and update. Another computing environment that does not appear only until very recently is the cloud computing. Basically, the cloud computing environment, it consists of traditional operating systems plus VMMs, which means virtual machine managers, and also plus network connectivity, and also it provides some special tools called cloud management tools. And as shown in this figure, it shows a typical cloud computing environment. There we can see in the local company, we have different kind of servers. And inside those powerful servers, we actually run virtual machines. That's why we need the VMMs. And also, inside those virtual machines, it still runs the traditional operating systems. And run those in these operating systems, we can run different kind of applications. And those applications can provide services to either local users still within the local area network, or even remotely for those other users they actually connect from the internet. And also, to make the local area network safely enough, not being attacked and being threatened by malicious users from the public internet, we also need to put a firewall there to better protect the servers and the local area network. And another thing is that we also, in a cloud computing environment, we also need a load balancer, which is a special computer can help distribute different traffic, different requests from the public internet to different servers running inside the local area network, so that we can avoid all the request traffic go to one server, make that server overloaded, while that other servers, they are just idle there and waste the energy and waste the money, right? So that is the typical cloud computing environment. And again, how can the users to talk with the cloud servers in this environment? We use the interface. And the cloud customer interface may be different from different type of cloud, which we will talk briefly next. So basically, there are different types of cloud. For public cloud, those cloud they are fully open to the public user from the internet, and mostly user will be charged for the time or CPU cycles they used on the cloud and pay for that. And also, there are some private cloud, they are only available within certain range. For example, the cloud within our university. They are only open to the students, to the faculty, to the staff inside the university, but not open to anyone outside of the university. So that is a good example of the private cloud. And in the real world, we may have those hybrid cloud, where part of the system work as a public, open to the public, especially when the server is not used by by the users from inside. But still, part of the system is reserved only usable by the user inside, so that's why it is called a hybrid cloud. And also, the cloud computing environment can be further divided by the type of services they provide to users. So for SaaS, that is shortened for software as a service. So where basically the server just provide some software, some application over the internet so that other users can use that software, use that application through the internet. One good example is the Microsoft Office 365. So basically you can use everything through the internet without needing to pay the money to purchase the whole software back and install that on your computer, right? So you can see in this case, the cloud customer interface is just a very simple software interface so that you can just get into this interface to use the software through the internet. And then the next type is PaaS, shortened for Platform as a Service. So there, basically, it provides the user through the internet a platform environment. One good example is the Google Cloud, where it provides you a Python programming environment. Inside the environment, you feel like you are doing Python programming on a single computer, but actually, in fact, it is not the case. Actually, it is the whole Google Cloud try to provide you the service, try to provide you the platform as a service. So you can see there, the cloud customer interface is just a platform interface. And the last one is IaaS, shortened for Infrastructure as a Service. There, what the cloud provides the user is simply the virtual machines. So basically, you can just access another computer, which is actually a virtual machine running inside the cloud remotely via the internet. And on that virtual machine, you can install any software you want, build any platform you want, and then just use it remotely like a computer belong to yourself. So you can see in that situation, the cloud customer interface is actually the general infrastructure interface, basically provide user access to a virtual machine where you can just use the virtual machine like you use a real machine locally on your own computer. So this is the different types of the cloud computing environment. The last thing we will talk about in this chapter is the open source operating systems. So open source means we not only made available the binary code of this operating system to be used by other users, we also made available of all the source code to the users so that they can free to modify the source code for their own purpose and then use those source code to further generate new operating system or provide new features to the operating systems. So this is actually counter to the copyright protection and the digital rights management movement. This movement is started by the Free Software Foundation, and sometimes called copyleft, counter to copyright, or it has a more familiar name to you. It's called GNU Public License, or GPL. Maybe for most of you, while you do the programming, while you use piece of code from the internet, you may also find the GPL at the beginning of the uh, code you downloaded from the internet. And actually, next slide will show an example there. And also, we have a number of examples for the open source operating system, like the GNU Linux, and actually also the Linux you used in the virtual machine, that is also an open source operating systems. And also, another interesting thing is most of you use Mac OS, and you know most of the Mac things, they have copyright. You cannot just simply get the source code there. However, a piece of the core part of the Mac OS is actually open source because it uses BSD Unix. So you can actually download and find the source code for that piece of the core part inside the Mac OS operating systems. And also, Android is open source, so if you really want to know what happened inside the Android operating system, you can just download the source code from the internet and then see what happened there, and also make the modification by yourself. Okay, now you may wonder, Dr. Wang, why we have open source operating system and closed source operating system, and which is better? And actually, there are trade-offs on those things. So, for example, open source operating system allow users to quickly develop new features for the operating system by themselves. Sometimes they may want to customize the operating system for special purpose, and open source surely allows them to do the modification much quickly and efficiently. They don't need to wait the company to make those modifications, right? On the other hand, let's talk about the service. So you can see most of the time, the Windows it runs pretty stable and also runs provide you a lot of different kind of applications. And also when you purchase those applications, when you use them, most of them are quite stable, are relatively stable, and have much less bugs, right? However, for open source operating system, well, you download the operating system from the internet, then you need to be careful, because if the user who provides this open source operating system is not some expertise, then you may wonder, okay, can the software run stable? Would there be a lot of bugs there? Would it have any security issue, any protection issue there? So that's another trade-off between the open source operating system and the closed source operating system. So normally, closed source operating system is provide you more solid software. It has much less bug. It is well maintained. And also, if a bug is identified there, most time the provider will fix this bug as soon as possible by providing those new update there, right? However, for the open source operating system, it may not be well maintained, and it may be modified by anyone else. So sometimes it's hard for you to determine whether you should trust this open source software or not, right? On the other hand, of course, for closed source operating system, it's very hard to add new features, especially for normal users. However, for open source operating system, you can quickly understand what's happened there because you have all the source code available, and also you can quickly add any new features you want there, make the modification as you want and see what's happened there, and get the result pretty soon, pretty quickly, right? So again, that's a trade-off there. And for us, why we choose Linux instead of Windows as the example in this course, also because of the open source operating system. Because if you want, you can find the open source, you can find all the source code for the Linux, see how it implement different major components inside the operating system. Like we just discussed, the process management, the main memory management, the storage management, the I/O management. And then if you are interested, look at what happened there, and you can learn more about how those things can be done in real world. And like I mentioned, the last slide shows an example of the GPL in the real world, and you may already see this GPL many times on the source code you download from the internet. So I won't go through details there. So maybe later, if you want to author some new source code based on some source code downloaded from the internet, you may also need to include this GPL in your own source code at the beginning of your own source code to further follow the copyright requirement there.